So, welcome to the 29th Theoretical Physics Colloquium at ASU. I'm very glad to present Professor Giorgio Torrieri from Glavatagging Institute of Physics at State University of Campinas in Brazil. He got his PhD in 2004 from the University of Arizona. He had several postdoctoral positions. 2004, 2006, he was a postdoctoral researcher at McGill University. Between 2006 and 2008, he was an Alexander von Humboldt Fellow at Johann Wolfgang Goethe University in Frankfurt. He was then a research fellow at the same Goethe University between 2008 and 2010. Between 2010 and 2014, he was a visiting research scientist at Columbia University, and afterwards he joined the State University of Campinas in 2014. He is also serving as an assistant editor of the European Physical Journal A, and he received an award of outstanding referee from APS Journals in 2014. And with that, I will give the microphone to you, Giorgio.
Okay, thank you very much for the invitation. I'm attending this colloquia very regularly, and it's a great honor and a challenge to speak here because the standard is very, very high. This is a bit of unusual in the sense that this is a very speculative talk. Don't feel free to disbelieve everything I say in the second part. If you believe it, great, I believe it. But the point is it is speculative and incomplete. But please, I hope to convince you that at least the issues that I'm raising, the questions I'm asking are legitimate, even though the answers I might be giving are wrong. Also, it's a bit of, it's not certainly not an official follow-up, but last week's seminar by Pavel Kovtun gave an excellent introduction to some of the same issues I'm talking about. I am talking about this in a slightly orthogonal context, but I really recommend, if you haven't seen it, to watch it on YouTube to understand some of the context of the questions that I'm asking. And there is also a workshop going on the same, which touches the same subjects right now, and you can see the talks there. So my point is that experimental data gives us a necessity, not so much to rethink, not necessarily to rethink hydrodynamics, but to rethink the approaches from which hydrodynamics comes from. Because hydro has been found exactly in situations where these approaches are supposed to fail. And the only way so far I can think of to rewrite hydrodynamics so that it reproduces usual hydrodynamics, but might also be applicable there, is by using two concepts. One is the Zubarev statistical operator, two concepts from condensed matter physics, which haven't been applied so far to deriving relativistic hydrodynamics, namely the Zubarev operator, namely expanding your, if you want, microscopic density matrix into an approximate equilibrium, which one would describe by the Zubarev operator, and the rest, which in about equilibrium can be derived using Crook's fluctuation theorem. This is an alternative, this aims to be an alternative derivation of hydrodynamics as an effective theory. And I would like to, it's the same hydrodynamics, it's just seen differently. And I would like to offer an analogy that QCD can be described by Wilson loops or by chiral perturbation theory. In some case, for some situations, one is better than the other. For some situations, one is intractable, but the bottom line is that it's the same QCD. So why are we interested? This is the second colloquium on relativistic hydrodynamics we have. Well, most of us know why we're interested. It got in the New York Times, for heaven's sake. Rick scientists have served up the perfect liquid. This was already 16 years ago. They made coffee mugs, press releases, articles, and it comes down to, it comes down to calculations such as these. It seems that angular anisotropies of the momentum of the outgoing particles follow the shape anisotropies one expects in the initial state. And this suggests that the system made is a continuum rather than a dust of particles that just propagates. And if you put some numbers on it, like these people have, it turns out that the viscosity, it turns out in relativistic systems, you distinguish between these two limits by things like viscosity and relaxation time. And it turns out that the viscosity needed to describe the data could actually be zero, and certainly has to be pretty small. I'll explain a little bit more about what this means later. So this has ignited a lot of interest within theorists and phenomenologists into relativistic hydrodynamics, and on the theory side, into deriving relativistic hydrodynamics from microscopic theory. So what is it? It's an effective theory, and it's built around the idea of fast local thermalization. So if you divide the system into cells, every cell thermalizes fast with respect to the gradients. And then we all know from Lifshitz and Landau what the equilibrium energy momentum tensor looks like. It turns out that it's a closed system of equations. If we also put in the equation of state, there is some frame in which it's isotropic. And then just from conservation laws and from an initial condition, we get the dynamics. This is true if thermalization is instantaneous. This is true if thermalization is instantaneous. If it's not quite instantaneous, we divide the energy momentum tensor into the equilibrium part and the rest, and then we expand the rest around gradients, because that's what you do in effective theory. Effective theories are built around scale separation, and here the scale separation is something called the Knudsen number, which is the microscopic over the microscopic scale, the mean free path divided by, basically multiplied by the gradient. And then Navier-Stokes comes with the Knudsen number 1. Israel-Stewart, with some arm waving, you can say that it comes with the square of the Knudsen number. That's the causal theory. And then, you know, there'll be an infinite tower of states that you can derive from the usual field theory techniques. What's wrong with this? Well, last week, we had a great explanation as to why and where and in what situations this fails. I would add that it's a classical theory. So there are no fluctuations, either thermal or quantum. And also, of course, we calculate in some perturbative limit, which in this context means linearized hydrodynamics. But the underlying system is strongly coupled, probably, since equilibration time scale is small. Is that a problem? Well, for instance, the other reason why everyone got so excited is because for a while people talked about quantum lower limits on viscosity. So people who worked on hydrodynamics thought that because of essentially underlying quantum mechanics, viscosity cannot be zero. You cannot have a really ideal fluid. Thermalization has to happen at a certain time scale. This was actually done in the 80s by Pavel Danielowicz and Miklos Gulashi using the Boltzmann equation and essentially using the uncertainty principle and plugging it into the Boltzmann equation, and you find that E over S is something like 10%. And recently in the 2000s, right about when experimentalists found these experimental results, you have the very famous KSS bound that if you have any classical gauge gravity duality, E over S becomes 1 over 4 pi. 1 over 4 pi is about the same as 10%. So this really looks like these two limits are opposite. So it looks like we've got something universal. This is a law of nature. Viscosity has to be small, but cannot be zero. And it seems to be close to experiment. End of story. Well, this might be a profound principle, but for now it looks more like Heisenberg's microscope than von Neumann quantum mechanics. Because both of these theories are unrealistic, and they're actually unrealistic in a very similar way. Danielowicz and Gulashi used the Boltzmann equation in a regime where it's far from clear something like molecular chaos works. And KSS has this conformal planar strong coupling system. The funny thing is that they're unrealistic, but they're unrealistic in a way that is ultimately very similar, because molecular chaos and the planar limit are in some sense the same sort of expansion. You decouple the really microscopic scale, your heat capacity, your microscopic degeneracy, from not just gradients, but also from the mean free path. So the number of the microscopic number of degrees of the coupling constant is large, but the microscopic number of degrees of freedom definitely has to be bigger than the coupling constant. So in this sense, I mean, you know, people, a lot of people make ironies about, yeah, 3 equals infinity, blah, blah, blah. Well, 3 equals infinity works works for many things, but here, this is exactly the same, this is somehow exactly the same approximation. The degeneracy of this microscopic degeneracy of the system is large, not just with respect to 1, it's large with respect to the mean free path. And unfortunately, experimental data is a harsh mistress, because experimentalists at the LHC was turned on and people started looking at higher multiplicity PA and PP collisions. Then they looked at them at RIC, and lo and behold, they found that, somewhat to a surprise of most people, that small systems are exactly the same, are exactly as fluid as big systems. This was a great analysis done by the CMS collaboration that I kind of use as reference. I'm not going to explain what they do. They do very complicated azimuthal correlations of many particles, and PP collisions with 50 particles and AA collisions with, you know, thousands of particles look remarkably the same fluid, just as collective. So this thing that I was talking about infinite degeneracy, experimentally, this looks like weird. This looks weird because certainly systems with 50 particles do not have infinite degeneracy, and yet fluidity is, small viscosity seems to be insensitive to this. What do theorists do to explain this? Well, this also gave rise to a lot of theoretical and phenomenological activity, and it's usually centered around concepts like hydrodynamization and fake equilibration and stuff like this, where you basically take the same microscopic theories, the Boltzmann equation and also ADS-CFT, you solve a very anisotropic system, usually with profound symmetries. Usually they're one-dimensional systems because they're azimuthally symmetric and blah, blah, blah. And lo and behold, it turns out that something like hydrodynamic attractors emerge. So even for large gradients where a Knudsen number is much bigger than 1, hydrodynamics seems to work surprisingly well. And here, I really become very skeptical. And the reason is skeptical in the sense that I'm not convinced hydrodynamics can have vanishing viscosity. So it could be that viscosity is 0 and arbitrarily small systems give you fluids. I can believe that. I'm not going to believe that such systems obey the Boltzmann equation too. They might obey hydrodynamics because that's still not understood. I don't believe they obey the Boltzmann equation. And the basic question is exactly what I was saying before, large NC and ensemble averaging. For 50 particles and for a strongly nonlinear theory like hydrodynamics, it's far from clear that you can do ensemble averaging, that you can basically sample 10 events like one big event. And this is basically what molecular chaos is based on. In the same system, if you assume hydrodynamics, you assume local thermalization. If you assume local thermalization, you assume the equation of state. I think there is a minus sign here. But if you assume this, then you also have to assume the rest of thermodynamics. So you will have energy fluctuations, particle fluctuations, et cetera, et cetera. And they're approximately Poissonian. For 50 particles, it will be the square root of 50 particles, which for a nonlinear system can very quickly blow up. And this is something that, to my knowledge, it has not been consistently, to my knowledge, I have not seen a model that really tries to explain how can nonlinear hydrodynamics work against such small, but certainly not small fluctuations. And I'm pretty sure that hydrodynamization and fake equilibration will not solve this issue, at least because fluctuations don't have any symmetries. It's not enough to assume the average is symmetric. Fluctuations will be symmetric too. So, I mean, in such a system, there is a lot of things which are taken for granted that we have to throw out. One of them is the second law of thermodynamics. The second law of thermodynamics, so the fact that this guy is smaller than this guy and entropy always increases, this doesn't have to be the case for 50 systems. It has to be more likely. It has to be more likely, but the probability doesn't go to zero. And in pretty much all derivations of hydrodynamics from microscopic theories, this is sort of as a given. This is how people define entropy current. So either hydrodynamics is not the right explanation, which is certainly possible. I've also worked on competing models, thought about competing models in the past. However, I would caution against the idea that small and big systems that, I mean, there's people who say, well, the correlations in smaller systems are dominated by initial state effects and correlations in big systems are dominated by the hydrodynamic phase. The similarity of the small and big systems, to me at least, suggests that the underlying physics is similar. So either we are radically misinterpreting the data, or we're not understanding something basic about why is hydrodynamics working. What's the microscopic theory behind hydrodynamics? What is the role of fluctuations? And so on and so forth. Well, last week's talk by Pavel Kovtun actually gave an introduction to these issues and talked a little bit about this. The point here is that hydrodynamics isn't just an expansion around the Knudsen number, it has three length scales. When people talk about the Knudsen number, they talk about these last two. And the scale which comes with a planar limit in the molecular chaos is the first one, which is simply the distance between degrees of freedom. I mean, you can also define it non-perturbatively, but you basically pick entropy and pick the entropy density, sorry, and take it to the power of -1/3. This first hierarchy is what ensures molecular chaos and gauge classical duality. And what happens, the question is, I mean, this hierarchy has been studied to death, but what experimental data forces us to consider is the first hierarchy, which is certainly non-negligible, unless eta is 0 or something like that. And certainly even even if eta is 0, the remaining inequality, L micro versus respect to L macro, is certainly non-negligible in a system with 50 particles. So what gives? Well, I'm quoting Kovtun this paper by Kovtun, Moore, and Romashke. Pavel talked about it last week. The point is that one thing that you can think of is as viscosity goes to 0, sound waves propagate from -infinity to infinity. They don't decay, they don't dissipate. But what the Kubo formula that you use to calculate viscosity, what the Kubo formula does is exactly calculating perturbations of the energy momentum tensor. So these perturbations will affect what you get from the Kubo formula when sound waves don't dissipate much sooner than -infinity to infinity. And therefore, the Kubo formula needs to be renormalized. And what happens is, I mean, look at the last talk, it was explained very well, but the bottom line is eta over S will be bounded by something like temperature divided by this microscopic length scale. Because of the fact that if microscopic eta over S becomes smaller than this, sound waves will renormalize eta over S and eta over S will come back. Also, there will be an extra stochastic mode which will screw up Israel-Stewart hydrodynamics, but this is technicalities. I mean, this was a great work. My practical objection was, thanks, but you haven't been helpful. I'm trying to explain why do you get a fluid with 50 particles, and you've just showed me that there is an extra reason for hydrodynamics not to work in such small systems. So we have to think harder. This is a difficulty. This is a bug, not a feature. And so is there a reason why this could break down? Well, To renormalize this, you need an upper, you still need an ultraviolet cutoff, and this ultraviolet cutoff is basically this microscopic length scale, entropy to the 1/3. The point is, isn't assuming this Pmax, isn't assuming this microscopic length scale and assuming that it cuts off sound waves a little bit circular. It's reasonable, don't get me wrong, it's not obviously wrong, but the bottom line is you are assuming a microscopic scale, you get a microscopic cutoff. This system is strongly coupled. This Pmax might be something different than what was assumed there, than what was assumed in this paper. How could we investigate this? Well, hypotheses like eigenstate thermalization, I mean, there was a nice paper written about this 2 years ago by these people here. Essentially, we know Kubo formula, we know local Lorentz invariance, and just from these things, assuming that somehow the system thermalizes or looks, it might be a fake thermalization, but if we take the microscopic theory and assume that it instantly just thermalizes, we can get a microscopic density matrix or its equivalent for field theory just from this requirement. And then we can, in theory, feed this into Kubo formula. We can try to use the Kramers-Koenig relations. We can try to use local Lorentz invariance or what is called the gravitational Ward identity. And we might be able to get constraints from viscosity from here. This is what these guys tried to do, but they also had to assume things like a correlator. I mean, this was a path towards this. You can do this for the microscopic theory that instantly thermalizes, but the issue is that hydrodynamics is also nonlinear, could also be strongly coupled and turbulent, and in fact, if you think about it from a Lagrangian point of view, it certainly will be, because vortices, if you write hydrodynamics in terms of a Lagrangian, you will discover very quickly that vortices have no energy gap and they also don't propagate, which basically means that the vacuum is generally unstable against their formation. So just because you think that the microscopic system is strong enough to instantaneously thermalize doesn't mean that doesn't give you everything, because macroscopic and microscopic degrees of freedom could talk to each other. What exactly do I mean by this? Well, a classical lower viscosity fluid is turbulent. We knew this since the 19th century. And in 3 dimensions, what happens is that low K modes cascade into higher K modes. If you assume that everything is classical, and if you assume that there is this fourth scale, which is called eddy, actually it turns out that there will be no scale, because if these 2 scales are infinitely separated, Kolmogorov found this basically dimensional analysis cascade, which works reasonably when the scales are alienated. And this shows that this shows, at least for the non-relativistic incompressible flow where turbulence happens, this shows that the system is in some sense strongly coupled also at the macroscopic level, because what happens is that every energy scale gets filled. This is, of course, a quintessentially classical system, because it doesn't assume Planck's law. It assumes that for an arbitrarily high K, you can have an arbitrarily low perturbation such that the energy content of this perturbation is arbitrarily low. So quantum mechanics, if nothing else, has to cut off this cascade. But it will cut it off. As you can see from this vortices stuff, it will cut it off with typically in a non-perturbative fashion. So it's not something that we can calculate. I have worked on this. I mean, I've started working on this at Columbia. Endlich et al., Professor Alberto Nicolas and his group started seriously investigating corrections of fluctuations to hydrodynamics using Lagrangian techniques, which potentially are not perturbative. What happens is that you can write hydrodynamics in terms of co-moving coordinates. If you do this, you will get a Lagrangian. If you do this, you will get a Lagrangian. And if you get a Lagrangian, you can do functional integrals. And you can try to answer the questions you can try to look into the formulas I was putting in here using functional integral techniques. This was a lot of work. There were some accomplishments. I mean, I wrote an overview paper. I wrote an overview paper about it here. There were 5 or 6 papers we published about it. There was insight. We could derive something like Israel Stewart from Ostrogradsky's theorem. We extended this to polarization and made the conjecture that polarization, so the spin alignment, if you want, could provide a soft dissipative gap to stabilize vortices, to solve the problem of stabilization of vortices. I'll talk about this the day after tomorrow at the seminar if you guys wanna, if you're interested. However, it doesn't, this is still a coarse graining, which is based on, you know, I mean, if you don't know how to do perturbation theory, you do this on the lattice, and we did. Here's a lattice paper about this. It's still a coarse graining where you try to do where you divide your continuum into little cubes and you try to do the functional integral on these little cubes. Incidentally, vortices for hydrodynamics without polarization, it looks like the vacuum with vortices and without vortices exhibits a first order phase transition where the free energy has 2 minima. And the first order phase transition is in the microscopic degeneracy. If the microscopic degeneracy is big enough, then vortices go away, but otherwise you will have this turbulent hydrostatic phase. So ultimately, this provides some insights, but I want the volume element. I want the degrees of freedom inside the volume element and the collective excitations to talk to each other. And I want potential nonlinearities. And I want potential nonlinearities to be incorporated in this talking to each other. And it will not work because the effective coupling constant of hydrodynamics is proportional to the momentum exchange. These will be deviations from the Kolmogorov cascade. For vortices, as I said, the Lagrangian has no kinetic term. It only has a time derivative. So there is no S matrix and it's strongly non-perturbative. There are hints of phase transitions. And basically the question of what happens to even a hydrostatic limit when the system is small enough that you have little atoms here and it's collective enough that you have little waves here. What happens if these things talk to each other? This is a very difficult question for this reason. Coarse graining doesn't seem to work. In fact, I mean, this looks like something that only I'm interested in. But it's a basic, to me, it's actually a very basic question of statistical mechanics too. And the reason is, I mean, if you just take a bucket of water, take a bucket of water that isn't doing anything, a completely still bucket of water, give it to a statistical mechanicist, and they will tell you, oh, this is easy. I can write a partition function for this. With the van der Waals equation of state, I can even solve it. I can do yields, I can do fluctuations, I can do temperature fluctuations, volume fluctuations if it's somehow floating in space, chemical potential, susceptibility, I can calculate everything. So you take the same bucket of water and you take it to a fluid dynamicist or a mathematician doing fluid dynamics. They will tell you, well, this is an equilibrium state of a very difficult equation that we can perturb in an infinity of ways because we can shake this bucket of water in an infinity of ways. And in fact, we still don't know if this equation makes sense, if the Euler equation or the Navier-Stokes equation and the non-relativistic limit have eternal solutions. This is one of the clay problems of mathematics. So we have the same bucket of water, we have the same physical system, and physicists and statistical mechanicists looking at global equilibrium and fluid dynamicists looking at local equilibrium, in a sense, live in different universes. They are approaching the problem in very different ways. And in fact, if you look at dissipation, they're inverse of each other. In the sense that if you have a large viscosity, the system is not in local equilibrium, but it will reach global equilibrium very quickly. And vice versa, if the limit of viscosity goes to 0, if the limit of viscosity goes to 0, the system will be in local equilibrium, but will reach global equilibrium at asymptotically long times. So there are two ways of looking at the problem. I mean, this is something that an undergraduate who asks uncomfortable questions will ask. They're like, I'm taking a statistical mechanics course, I'm taking a fluid dynamics course. They both showed me a bucket of water, but they're describing them in very different ways. And they really are very different ways, and mathematicians have been worrying about this in a slightly different, their way of thinking is of course very different, but they have something like coarse graining as well. Mathematicians, for people who read their literature, call this weak solutions. I mean, they're trying to show that Navier-Stokes equations have solutions. The problem is that you might have integrable discontinuities where derivatives diverge. Mathematicians don't like it, so they integrate both sides together with a smearing function, and this allows them to treat divergences in analytical ways. This has been going on since the 30s, and it actually turns out the problem is still unsolved, but there are some very interesting stuff happening there. And this question of incompatibility, I think, is really profound because of things like, you do have things like what are called nightmare solutions, what mathematicians call wild or nightmare solutions. So it turns out that there are solutions to the non-relativistic incompressible Navier-Stokes equations such that you have a cup of coffee in the middle of the night, and then non-integrable singularities happen, and the cup of coffee becomes turbulent, and then it dissipates again to have the same cup of coffee. This is what's called wild and nightmare solutions. Of course, these are not really important if you are a physicist. They're unphysical. And if you go back to the statistical mechanics person, they will immediately tell you that this is unphysical, because if this was possible, they would break the second law of thermodynamics. We could put an engine here and it would do work on these nightmare solutions. So obviously this cannot happen. So what does this mean? This means we're not mathematicians. This means we're physicists. I don't really care if eternal solutions exist as a physicist. I mean, I'm not smart enough to be a mathematician. I do not really think that, I'm not even that excited about the questions they ask. However, these questions can tell us something about physics. The point is that statistical mechanics of microscopic degrees of freedom that thermalize on a very fast scale, and hydrodynamics of a coarse-grained system which obeys continuum mechanics, these two theories need to somehow be brought together in a consistent way. It has not been done yet. Coarse graining has problems with it. And experimental data tells us that the system where this needs to happen, it should be applicable for comparatively small numbers of systems, like proton-proton collisions with 50 particles, superfluids of like 10,000 particles, like in the unitary limit, and so on and so forth. This looked like abstraction. However, I am going to quote my last experimental result in this talk. There was this very nice observation 3 years ago, which made it to the cover of Nature, that the collective motion of vortices and heavy ion collisions polarize lambda, microscopic lambda particles, and now we know vector mesons which come out. Lots of pretty pictures, such as this one, was made about this. I mean, it again made headlines about subatomic swirls, but the system is still not understood. And the reason it's still not understood is because it exactly falls in the class of systems I was worried about. I mean, what this shows, like, there were people at the time, there were theoretical physicists who were like, yeah, it makes a bunch of pretty pictures, but what does this tell me about the quark gluon plasma? Well, to me, it tells me that you can't just think about this in terms of billiard balls, or at least non-rotating billiard balls. You have very non-trivial talking between microscopic and macroscopic degrees of freedom going on. And you will have feed down from collective excitations to microscopic excitations. And we need an effective theory that accounts for such a weak feed down and for such a back reaction. So what are we going to do about this? this was the end of my introduction with the questions. Now I will try to provide the answers. So every theory, every sort of stochastic theory, I should say, needs a state space, and an evolution dynamics. I think that one might be able to write a theory that could answer the issues that I just finished raising with two ingredients. One is the Zubarev state space operator, and the other one is the Crooks fluctuation theorem, which is something that many mesoscopic physicists and theoretical hydrodynamicists know about, but it has not really been used extensively in our field yet. And the reason that this can be done is because these two guys provide us a way to take T mu nu, to take the energy momentum tensor as an operator, and decompose it into two operators at the operator level, not at the level of the averages, but at the level of a statistical operator, in such a way that this guy continues to be a statistical operator and this guy becomes a statistical operator. So what do I mean by this? Well, Zubarev took the grand canonical partition function, covariantized it, except he was working on non-relativistic stuff, but you can also covariantize there. And he basically took the density matrix and found the density matrix for an ideal fluid, in motion. So what do you have? You have this beta, which is the, flow velocity divided by the temperature. You have the energy momentum tensor, and the Boltzmann factor, energy divided by temperature, nicely covariantizes into this. And if you believe in local equilibrium, i.e. locally you obey the KMS condition, so time is circular, time is periodic, this is pretty much inescapable. So the Boltzmann factor factorizes into this. The density matrix will look like this. This guy here is the partition function. Of course, it diverges for quantum fields, but that's okay. Everyone else does this, so I can plead. And the only thing that is left, which is sort of interesting, is the foliation. So those who do Cooper-Frye formula, you basically foliate the whole of space-time using a tau, a proper time, which could vary, and a space-time hypersurface. And this guy here will provide a volume element. Oh, by the way, I should say that for the rest of the talk, I will not talk about chemical potentials for simplicity. It's easy to extend this to chemical potentials, but I'm not going to do this here. So basically, the density matrix in a state of local equilibrium, given a foliation where the state is in local equilibrium, will look something like that. And this is nice, because this object here in principle contains both microscopic and macroscopic degrees of freedom, both of them. So what do we do? Well, if the system is not in perfect local equilibrium, we can sort of say that it's an approximate local equilibrium, and then we can coarse grain, which is what these authors did here. And if we coarse grain, we get a gradient expansion in beta mu, which reproduces the Euler equation. It reproduces the Navier-Stokes equation. But that's nice. We already had that with other approaches. It's nice that this approach is consistent. Second order, so Israel-Stewart has not been done yet. There is probably a way to do this. Because the beta mu here is a gradient. In this work, it's a gradient expansion in beta mu only. But remember that you also have a foliation. Foliation is arbitrary. In general, it's not parallel to beta mu. If the system has vorticity, then differential geometry tells you that these two guys cannot be perfectly parallel at all points. So at most, this guy here is approximately parallel, and it's arbitrary, and therefore probably there will be an arbitrary small p mu nu. I started working in this direction. However, this will reproduce Israel-Stewart, but as I said, we already have Israel-Stewart. I want to use this to answer, can one do better? And I think one can. And here I'm going to say, I mean, what I'm going to say here is actually probably the most controversial bit, and there are people convinced that you can't really do what I'm trying to do, but bear with me. The point is that the Zubarev procedure might allow you to somehow split the operator. What does it mean to split an operator? Well, it means, and this is exactly what we, in my language, what this means is that this guy here will be, this guy here will be described by one partition function. This guy here will be described by another partition function. The two partition functions are correlated. And what this means is that, in particular, the equilibrium part of the partition function will have all possible microscopic and macroscopic correlations. So both fluctuating sound waves and microscopic fluctuations, and they will all be encoded in this guy here. They will all be encoded in of the equilibrium part. They will all be encoded in derivatives of the equilibrium part of the partition function, which is exactly what I wanted, which is exactly what I wanted before. The fact that they're close enough essentially means that the total partition function will be dominated by the equilibrium part. Non-equilibrium part, the most likely configurations will be ones where either this guy is small, and configurations where this guy here are large are possible, but they are unlikely. And this is why I was saying this might incorporate the non-exactness of the second law. Once again, it's still this this division is still arbitrary. I mean, the physical observable will still be the sum. So how do we do it? Well, we for any flow field, for any possible flow field, we can define a partition function perfectly in equilibrium with respect to the flow field by basically using the Matsubara procedure. We make time periodic, and we do a functional integral on the lattice or whatever, and we do a functional integral with the microscopic Lagrangian thermalized. And this is going to be the partition function, and this is going to be the partition function that gives us the equilibrium part. This can be done for any ensemble of T mu nu. Here, when I use hat, I mean statistical ensemble, except when I forget. Here, I forgot. So for any configuration of T mu nu, you might be able to select a B mu, where you can make a partition function where this guy here approximates this guy. It will not be unique, of course. I mean, this is something that exists in your head, but hopefully you will be able to make such a choice. Okay, so if this guy here is well approximated, if you can choose a flow field that with a temperature that depends on x mu, with a flow field that depends on x mu in such a way that these two guys are more or less the same, you might be able to approximate the partition function. You might be able to approximate the partition function by the equilibrium partition function defined by a Zubarev flow. Defined by the Zubarev flow. So any density matrix can be separated by this. Hopefully, if the system is strongly interacting and close to equilibrium, this will be the dominant component. Incidentally, I mean, the sources that give you cumulants and fluctuations are the shape of the sources can be related to this meaning that mathematicians use for weak solutions. So there might be, if we make mathematicians believe in functional integrals, which they generally, in functional integrals in quantum field theory, which they generally don't, they might be able to do something here. Anyway, the question is, hopefully if the system is close enough to being locally thermalized, if the system is strongly interacting, then this guy here will approximate this guy, and we can use this guy to be left over. The question is, what happens to this guy? What is the dynamics? What is the dynamics that controls the evolution of this guy? Well, here we know what entropy is. Here we know what entropy is. It's the, it can also be taken from the partition function, from the equilibrium part of the partition function. And we also know from Israel Stewart hydrodynamics, where the dissipative part, it's not an operator, but they are independent degrees of freedom. We have a definition of entropy current, which is not dependent on local equilibrium, which is something like this. So the entropy flow across a foliation hypersurface, which is this unit vector here, is given by something like this. You have this tensor here, it's divided by temperature, and it's multiplied by the gradient. The point is that this is a quantity. This is nice because these are independent degrees of freedom, but we also need this guy here to fluctuate. We need entropy to increase most times, but not always. And we need this most times, but not always, be tuned to such an extent that any approximately local equilibrium state will go to some kind of global equilibrium state. So what do we do? And this is where one goes. I mean, I'm taking this image, and this is where one takes inspiration from statistical mechanics applied to nanosystems, statistical mechanics applied to things like nanosystems and protein folding, and one tries to use something called the Crooks fluctuation theorem. This is an image from a talk by Gabriel Landi, which started my interest in this, and I recommend looking at his talks on the web. I mean, he gives very nice introductions about this whole field, and if you want an in-depth introduction that doesn't depend on my speculations, then I recommend his talks. So what is Crooks fluctuation theorem? It's a theorem which has been proven in a class of systems such as quantum systems attached to a thermal bath, Markovian systems, basically. These are the places where it was being proven. And it says simply that if you have a system that does work, like, you know, a protein pushing back against a bath or a nano engine, the probability of a system moving forward, so the probability of a system doing work against the bath versus the probability, which increases entropy, versus the probability of the system moving backward. So the system, if you want, violating the second law of thermodynamics, the ratio of these two guys is going to be the exponent of the entropy. And here, most of the people in our field who learned statistical mechanics from Boltzmann will be like, this is a theorem, this is obvious. Entropy is the number of microstates. Well, it's intuitively very plausible, but it's actually far from obvious because this system is nowhere near equilibrium. It's in contact with the thermal bath. It's a mesoscopic system. What work means is something that people who work in this field actively argue. What work means, it actively argue about. So in this, and it looks like it's really valid for systems which are far from equilibrium, but somehow where microscopic fluctuations decohere. So for example, the quantum system is in equilibrium with the thermal system, like with nano machines, like with protein, and for Markovian systems where you don't have entanglement, which is something similar to thermalization, to microscopic thermalization. So the question, using this Crooks fluctuation theorem, you can prove, and this is what these people here do for part of their scientific career. This is a very beautiful paper that they published last year in Physical Review X. Using Crooks theorem is very nice because you get the equivalent, you get thermal uncertainty relations, not quantum uncertainty relations, but thermal uncertainty relations. So basically, limits of work a microscopic system could get, a microscopic system could get because of the fact that the system is small and the bath, the equilibrated bath the system is in equilibrium with is also fluctuating. And they do this by a very similar procedure to what I was talking about before. They have the locally thermalized part of the density matrix, the non-equilibrium instantaneous density matrix, and the Crook's fluctuation theorem forces this relation on them, where this guy here is related to the entropy production, And they have something similar to our Kubo formulae. But they're not a fluid, they're not a field, they're a quantum mechanics system. So basically, in this work, they've done something very similar to what I wanted to do for a fluid, but they've done it for a quantum system. I have local equilibrium because the KMS condition applies for the equilibrated part of the density matrix. You have separation between local equilibrium and between the equilibrated part of the non-equilibrium part at the operator level, and you have relation between them. And this is why I'm saying that so what's the diff? That this way of doing hydrodynamics might be similar to Wilson loop coarse graining versus effective theory. Wilson loop effective theory does a gradient expansion and uses averages and uses 1-point functions, 2-point functions to construct an effective expansion. Here, we somehow resum all the microscopic operators. We somehow resum all the microscopic fluctuations, all the thermal fluctuations, all the effects of the microscopic length scale in the operator definition of the equilibrium part of the energy momentum tensor and the non-equilibrium part. Incidentally, people have used Dzerzhinsky's theorem on the lattice. I mean, this is a nice paper about this. And the context in which it was used is similar to what I'm talking about here. So I hope I convinced you. I hope I convinced you. I'm actually coming to the end, but anyway, I hope I convinced you that applying Crook's theorem to Zubarev, that the key to answering the questions I asked in the first part is to apply Crook's fluctuation theorem to Zubarev hydrodynamics. Mathematically, if you played around with sort of multidimensional integrals in Minkowski space, this actually becomes easy. Unlike the statistical mechanics types, we don't have to argue what work is. Work is the energy momentum tensor contracted on our foliation. And it's very easy to get something like, the Crook's fluctuation theorem applied to foliation and hydrodynamics. And it looks something like that. In the small loop limit, you reproduce a Kubo formula. In the small loop limit, you basically reproduce, and in the small loop limit and in the foliation, where this guy here is where this guy here goes from spatial infinity to time infinity very slowly. From past infinity to future infinity in space, and also very slowly, it's easy to see that this guy here goes back to the Kubo formula that we're familiar with. If instead your foliation is space-like in terms of time-like, so you have two volume elements which are infinitely close to each other at the same time, you reproduce the first law of thermodynamics. So heat flow is going to be related to the logarithm of the number of microstates, which is the entropy. And when the number of microscopic degrees of freedom goes to infinity, and they also interact infinitely fast, all these probabilities should go to delta functions. And what you will end up with is the delta function of the entropy current. In other words, you will have a foliation where the entropy current is conserved. And this is exactly the definition of ideal hydrodynamics without chemical potentials. You define an entropy current, you define the flow, and the entropy current among the flow is zero. So putting together Zubarev hydrodynamics and the Kubo formula gives you the right limits, where these limits are relevant, which is sort of obvious because the Zubarev hydrodynamics reproduces the usual hydrodynamics, and Crook's fluctuation theorem is basically, to me at least, if you think about entropy microscopically, it's the Boltzmann definition of entropy applied to adjacent configurations. So this is reasonable. Can you do more? I think so. The point is that, as I said, the point of these microscopic entropy relations is that it allows you to derive thermodynamic uncertainty relations. It allows you to derive thermodynamic uncertainty relations. The uncertainty relations are of this form here, that the entropy, that the rate of growth of entropy, which is which is a measure of the efficiency of your microscopic engine. The rate of growth of entropy, which is a measure of efficiency of your microscopic engine, is going to be equal to, is going to be bounded below by thermal fluctuations. It's going to be bounded below by thermal fluctuations. So if you make an engine which is very small and sort of very efficient while still being classical, thermal fluctuations will overwhelm it and it will not be so efficient anymore. And this is an operator form, exactly what Kofton, Moore, and Romachka were saying. This basically says that if your viscosity goes to 0, thermal fluctuations will produce sound waves, and these guys will dissipate stuff. So just copying maths from a nano-statistical mechanics system to a fluid dynamics system, we show that if vorticity is somehow small, sorry, not if vorticity is small, we can always divide flow. We can always divide flow into potential flow and vorticity, and then we can make our foliation as parallel to flow as possible by basically picking out the potential flow and flowing this way. Vorticity will be proportional to the co-moving metric. And if you just take these uncertainty relations and put them, this is not a proof, this is a suggestion, this is a conjecture, you're going to get something like this. And this is going to be where the constant is going to be related to the real and imaginary part of the correlator of the energy momentum tensor from the microscopic theory. And this is going to be, and this is something that a mathematician said is a dream for a different generation, understanding what is called anomalous dissipation. So basically rigorously understanding dissipation due to turbulence. Of course, mine is a conjecture. It's not a, it's not a proof that a mathematician would consider as a proof, but it might be a road to do this, to understand both microscopic fluctuations of a small system and turbulent responses to this when the small system is instantly thermalizing by using something like these uncertainty relations. What is nice is that when you use the gravitational word identity, which I suggested earlier, you actually, when you use the gravitational word identity and you put everything together in terms of functional integrals, you find that you can solve the partition function. Obviously, you cannot solve it on pen and paper. I mean, if you do, I'll be very impressed. But what I mean is that if you take a lattice and you model an ensemble of starting T mu nu, of starting total energy momentum on the lattice, you will have an algorithm. Which will be very computationally intensive, but it's a very well-defined algorithm. You will need an ensemble at every point of taking the energy momentum tensor, separating it into an equilibrium and a non-equilibrium part, evolving the equilibrium part using Zubarev, evolving the non-equilibrium part using the Crooks fluctuation theorem, putting them back together and coming to the next step. So this is going to be a lattice hydrodynamics, which takes microscopic and macroscopic fluctuations in the same setting. And maybe one day it will be done.
Giorgio, you wanted to tell me when the 1 hour will be? This is about.
Yeah, I see it. I will finish right now. I will finish. Just give me just give me 3 more minutes.
Take your time.
Yeah, there is a semi-classical limit, which should be similar to Israel-Stewart. However, fluctuations, decreasing entropy should have a role bigger than this Israel-Stewart term, which is something that has been talked about in the literature, and Pavel mentioned this last week. What next? Proving some of the things I said are correct, of course. One way to do this is to do a one-dimensional system where a lot of the ensembles I was talking about will be simple numbers. For example, the antisymmetric part. Well, the p mu nu is going to be just a field of numbers. Beta isn't going to be a vector but a number. It doesn't have vorticity. So these equations will be enormously simplified in one dimension. One can add polarization, chemical potential, rotation, acceleration. And I'm going to spend a couple of minutes talking about this because at the seminar, at the workshop in the last couple of weeks, this has been an intense topic of arguing. Because people have used Zubarev type approaches to obviously introduce chemical potential, but also to introduce vorticity and acceleration, And in fact, Becattini and collaborators and Prokhorov and collaborators have constructed a globally equilibrated state, if you wanted a passive non-inertial transformation, and they've constructed a density matrix for this. And it turns out that the generally does not obey the KMS condition. No one really knows if it's stable or not. And this is one of these issues where the discussion I had earlier about a physicist looks at the system one way, a mathematician looks at the system the other way. This becomes a practical matter because you will have a system which is in global equilibrium in the sense that it globally maximizes entropy, However, it's not in local equilibrium because in general KMS conditions don't apply. So it's not really clear what do you do with this system? How do you do a dynamics based on approximate local equilibrium? Which will reach this global equilibrium state that they're talking about? Well, Crook's fluctuation theorem might provide a way to thinking about this, because of the fact that the KMS condition, because of the fact that the detailed balance is, because of the fact that the second law of thermodynamics is actually valid locally, and also one has to remember that entropy is frame dependent, that entropy is actually frame dependent. In a non-inertial frame versus an inertial frame, you will have different amounts of entropy. I mean, the Unruh effect in general relativity is a manifestation of this. And the point is that using this Zubarev plus Crook's fluctuation theorem approach, microscopically, the system will obey in a foliation, the detailed balance, the exact conditions of detailed balance will be frame specific. But if you look at it over a large number of time steps, the ensemble of T mu nu configurations that I was talking about should obey detailed balance in every possible fluctuation, which is close to local equilibrium. And therefore, the system at the long time will reach a state where the KMS condition is microscopically valid, and that state will be stable because of the fact that the KMS condition enforces stability. And last but not least, because speculations are this last statement that entropy is frame dependent and detailed balance is foliation independent, even makes me hopeful that combining this with Ted Jacobson's microscopic entropy derivation of general relativity makes me hopeful that such a hydrodynamics, that the Crook's hydrodynamics together with general relativity will include fluctuations, which one could calculate essentially from Jacobson's horizon, from Jacobson's formula for the Raya-Shaduri for the curvature, for the entropy as a function of curvature, and it will incorporate fluctuations in a generally covariant way, foliation independent and generally covariant. So such a general relativistic hydrodynamics might be foliation independent. every tenured professor has to have a theory of everything. Ready, my theory of everything is that the universe is governed by Crooks. There is a lot of phenomenological evidence for this. This was, of course, a joke. And in conclusion, I mean, the Zubarev hydrodynamics together with Crook's fluctuation theorem is the only way I can think of building a hydrodynamics where microscopic degrees, strongly coupled microscopic degrees of freedom and turbulent macroscopic degrees of freedom talk to each other in a self-consistent way. This might lead to an anomalously fast equilibration, or might not. But the fact that ideal fluid behavior seems to be seen in comparatively small systems forces us to put this sort of questions at the center of our theoretical development, because up until now, the question of what happens when you take microscopic fluctuations and nonlinearity of hydrodynamics together, I haven't seen a convincing answer to this, and perhaps this is one. Thank you very much.
Well, thank you. Thank you for a nice presentation. Now we will have some questions. So are there any questions from the audience?
I have a question.
Go ahead.
So how would you, what kind of experiment would one do to check this theory?
Oh boy.
I mean, I was trying to think of one and I didn't think of one offhand.
No, sure. I mean, first of all, I haven't proven to you, this is not a theory, this is speculation.
Well,
for now. I'm the first person to admit it. So the experiment, for me, the experiments have already been done. We know experimentally that systems of the order of 50 particles behave, if you look at the right observable, they behave as ideal fluids. We also know that vortices in these fluids seem to polarize the fundamental degrees of freedom. In this case, they are vector mesons and lambda baryons. They seem to polarize the microscopic degrees of freedom. Up until now, there were phenomenological models which explain it. But these phenomenological models aren't really fully self-consistent. I mean, with the latter, for example, there is a very nice calculation that explains this by assuming you have an ideal fluid, you evolve the ideal fluid, and then you have freeze out, and in the freeze out, you add angular momentum to the Boltzmann formula. And you calculate polarization this way. And they actually fit experimental data pretty well. But this is inconsistent, because when you do this, you break detailed balance, because you assume that there was no polarization before and there is polarization after. So this isn't really in full local equilibrium. If this works, and if one can make a numerical implementation of this idea, and if you start with the ensemble of initial conditions you get from the initial state, which is something that people think they have under control, and if you reproduce experimental data, which is these many particle correlations which were observed by the CMS experiment, and if you reproduce something like this data, and you reproduce it in a way that doesn't make you violate the assumption that go into the hydrodynamics, such as, you know, you're doing hydrodynamics, but if you check the Knudsen number, your Knudsen number is 100, you know, then I would say that this theory is vindicated. You see what I mean? Mm-hmm. Because at the moment, yes, you can use hydrodynamics to describe systems of 50 particles, and you might get the data, but I do not see how this is self-consistent. The thing that I'm hoping to answer with this is, how is this self-consistent? You see what I mean?
Yeah.
Okay, any other questions from the audience? I actually, using the opportunity, I'll ask you, you were insisting saying this 50 particles, in general, in heavy ion collisions, you are producing thousands and thousands of particles. So when you're saying 50 particles, you mean a proton-proton, some low energy collisions?
Proton-proton.
Right.
Proton-proton. Well, what happens is, yeah, let me go back to the beginning just to tell you.
Yeah, I do remember this,
So
Bjorn Schenker and CMS, yeah, data.
The money plot is the CMS plot where they have proton-proton here, proton-lead here, and lead-lead here. This is where thousands of particles are, and this is where 50 particles are.
Right, but even in this case, I was sort of not sure that you could really treat it as hydrodynamics, even though there will be some kind of distributions looking like hydrodynamics. And you were saying in your talk that somehow you might believe that hydrodynamics works there, but you definitely don't believe that Boltzmann theory works there. I was actually confused a lot about that because usually it's the other way around.
Yeah.
So can you sort of expand on that?
Yeah. If you sample the theorists, usually it's exactly the other way around because everyone in our field likes transport. But if you look at the data, this is something that, the godfather of heavy ion physics in Brazil, Takeshi Kodama, I don't know if he's here, he actually always insisted about this before it was fashionable. He was like, look, if it's real hydrodynamics, you have to be able to coarse grain the system into cells, and you should be able to do ensemble averaging on every cell. And this assumption is also required for the Boltzmann equation. Actually, numerically, this is how the Boltzmann equation is calculated. You do things called the test particle method and such. So real hydrodynamics is if you should be able to do this. What is funny?
The equilibrium is one of the things that define hydrodynamics and which is not required in kinetic theory.
Yeah, but molecular chaos is required in kinetic. This is what I'm saying. So there are a lot of systems where kinetic theory is lousy and hydrodynamics works well. One of them is water. In water, hydrodynamics works, right? If you try to build a Boltzmann equation for water, you will probably fail because of the hydrogen bond, because the molecules are very tightly correlated. You do not have scattering in water. So to me, generally, this is why I always think of hydrodynamics in terms of thermalization, and every cell is fast. And certainly hydrodynamics is a limit of the Boltzmann equation, but it's also a limit of many other things. Certain circumstances, it's a limit of ADS-CFT. But there is more, there might be more things, and this experimental data really makes me think that the Boltzmann equation and ADS-CFT fail in a similar way, and it's exactly this. So if you coarse grain a system of 50 particles, you're going to have like 3 particles per cell. So are you going to say that you can do ensemble averaging with 3 particles? They don't have to be 3 particles. They might be 3,000 correlated particles whose entropy is 0 because the entanglement entropy. But you certainly cannot use the Boltzmann equation here.
Okay.
Yeah.
So next question, Arthur Lopes.
Hi, can you hear me?
Yeah, go ahead.
So just going further on this discussion you're having, you talked a bit about the correlations between micro and macro degrees of freedom. So I was thinking there is something to be said about the interplay between the hard and soft sectors or jet and hydrodynamics in that matter.
Sure, I agree. And in fact, in a previous paper, I actually suggested that one way to test if it's really,
Level.
there will be a, if you put in just naive dimensional analysis, right? The cross-sectional area is proportional to the inverse square of momentum exchange. So there's going to be a critical momentum. So there's going to be a critical momentum, like you say, for which faster billiard balls will go away. And this critical momentum depends on the Knudsen number. And this critical momentum depends on the Knudsen number. Given that in PA collisions, there doesn't seem to be any very little jet energy loss, given this, one would expect, for the reasoning you give, one would expect that high PT V2. So one would expect that elliptic flow at very high PT turns off in PP collisions faster than in AA collisions. Turns off in PP collisions faster than in AA collisions, for exactly the reason that you say, because PP collisions are smaller, the effective Knudsen number is larger, so the momentum, a smaller momentum exchange is enough to make the cross-sectional area too small, and this fast particle will just go away. You will still have radiative energy loss, but we experimentally know that in PA, energy loss is very small, and therefore V2 should also turn off. Well, in last year's quark matter, in Wuhan, the good old days, one of the most interesting results shown at that conference was, I think, the Atlas collaboration has looked at, using these cumulant techniques, they looked at V2 at high PT for small systems. And it turns out that V2, the critical PT at which V2 starts decreasing, at which elliptic flow starts decreasing, is completely independent of system size. Seems to be largely independent of system size. I don't understand this. I don't understand this precisely for the reason you say.
Well, maybe there is no hydrodynamics there. It's as simple as that.
Well, but then why is V2 as big in PP and in AA also at high momenta?
Has nothing to do perhaps with hydrodynamics, but it's a good question.
I mean, it could, is it energy loss? Well, it isn't, because jet energy loss has been measured in PA and it's not there.
Well,
I mean, it's a very good question, and experimentalists have been playing, in my opinion, experimentalists have been playing with that question, and we don't understand the results.
okay. Any other questions from the audience?
Sorry, Igor, if you could, or Giorgio Neustark, if you could give a reference to that Atlas paper you mentioned, the one you said they showed in quark matter.
Oh, Jesus.
Well, maybe he could send you later after talk.
Yeah.
Jamal, that was you, right?
Yeah, it's in the highlights. I'm sure that it's,
no rush.
yeah, it's in the highlights. I know that it's in the highlights.
I think it will not be practical to try to find it right away, but that was Jamal, so please send him the link.
Yeah, okay.
Thank you.
Any other questions? Okay, I don't see any other questions, so we will be wrapping it up. I would like to thank Giorgio again for a very nice presentation, entertaining, and thanks everybody for coming.
Thank you all. Thank you all. Fewer questions than usual, so either everyone believes me or everyone thinks it's nonsense.
Well, it's a little bit hard to grasp everything at once. I was trying to follow everything, but at some point, it seemed to me that you are pushing hydrodynamics where it shouldn't be.
Data is.
Well, data is
problem.
not telling you what's happening inside, I'm afraid. Data is really just some statistical, by the way, measurement. They collect a lot of different events to construct that thing. So in each and every event, if you pretend that there is something like Hydra, I would be very skeptical.
I would like to answer, because this is something so here, these 4, 6, 8, etc. is the number of particles, obviously within the same event they measure the cumulants. LYZ is Lee-Yang zeros. So in theory, this is sensitive to all particles of the event. And at the last quark matter, they've done cumulants of 12 particles. The degree of correlation, which in all systems is very quickly becomes independent of the number of particles. And this is sampled within the same event. I agree with you. I agree with you that for hydro to work, fluctuations have to be small, not just in an event, but in every cell.
Yeah.
We're not seeing this in data.
Well, you're inventing new type of hydro, I'm afraid. Anyway,
Yeah.
actually, it turns out we do have another question.
Sure.
Vertices, go ahead.
Yeah, hello. Could you please come back to the previous slide with the measurements? Actually, you said that you're not sure that hydrodynamic or kinetic theory is applicable in low multiplicity events. Yeah. So my question somehow is that we say, for instance, I have 10 particles at final state or 3 particles in final state. They are hadrons actually. But the hydrodynamic is applicable, could be, the initial state could be an off shell with full of degrees of freedom, a lot of degrees of freedom, but they are at some stage they hadronize and then you reach few particles. Therefore, if you say, we have low multiplicity at an event, it doesn't mean that we have not enough degrees of freedom at the initial state. Yes, for instance, in a very small system, if I have high energy density, they can turn into few number of hadrons at the final state.
I agree. I agree. The thing is that the final state number of particles, the finite number of particles counts the entropy. This is the Fermi entropy formula. You might have an infinite number of, you might have as many degrees of freedom as you want in the initial state, but they're all correlated. So they're, if you want, their number and their entanglement entropy cancels out, so that the total amount of entropy is the final one, because the second law of thermodynamics is probably valid, at least on average, at least probably. And if this is true, then molecular chaos cannot work. Then molecular chaos cannot work. This is why I was saying I might believe in hydro, but I don't believe in the Boltzmann equation for this reason. Because you cannot use one particle correlation functions. You have to use 2, 3, 4, 5, 6, whatever number of correlation functions, and no one knows how to write equations like that.
Okay. I hope we exhausted all the questions. And I think at this point I could stop recording.